So we're going to talk through chromatography in this video. Chromatography is used for separating and identifying the soluble substances in a mixture. Okay, so let's get that written here. It's used for separating, so it separates the mixture, but we can use it to identify the components and identifying soluble substances in a mixture. So it's a separating technique, but it's also one we can use to identify substances. Okay, so to identify the substances, we have to calculate the RF. Okay, now the RF is a measure of how far the substance moves up the paper in chromatography. Now, in the other chromatography video, we actually look at how to do chromatography, and it's a core practical, so it's one we really need to know about. So if you're not sure how to do a chromatography experiment, to get a chromatograph like this, watch that video. Okay, so what we're going to try and do here is identify in these two results of paper chromatography, one of these substances, A, B or C, is identical. Okay, we need to identify that by calculating the RF. So we need to calculate the RF for every different substance. So to do that, we're going to put a dot right in the middle of that bigger dot there, and the same up here, and dot right in the middle of that one. And we're going to measure how far that dot has run up that paper. So we've got a 0 right in the middle of that dot there. Let's just put a little line through that so we can see it. And we've got that down the bottom there as well. So we can see that's 3.1 centimeters, 3.1, and that one's been done for you because that's in the bottom there. Now we also need to measure how far the solvent front has run, how far the water in this case has run. So if you look at a result, it waves a little bit at the top, the water. So we're just going to draw a pencil, and you'll do it pencil in the when you do this in a core practical. I'm just going to use that pen there, but we do it in pencil because pencil doesn't dissolve in the water, you see. So all these lines at the bottom here are going to be pencil, and we're going to measure exactly how far that's run as well. Okay, and we can see it's come down at 5.9. We've got the 0 on that line at the top, and we're going to measure to the line at the bottom, 5.9. So 3.1 divided by 5.9 is 5.3. So we just need to do the same for all of these now. Okay, so dot in the middle of both those, and we can see that one's looking at 1.1, so that B has run at 1.1 centimetres. So that distance from there to there is 1.1 centimetres. The distance from there to there, what we said was 3.1, didn't we? So we need to measure how far all these run, okay, and we need to then divide it by how far the solvent front runs. That was 5.9, that distance there. And so 1.1 divided by 5.9. So I'll quickly put that into a calculator. Okay, and we have the RF for that one. 1.1 divided by 5.9 equals 0.1, we'll round that to 9, 0.19 equals 0.19. So let's quickly do this one here as well, this last one. So that's roughly in the middle there, isn't it? So we go from the middle of the dot to the middle of the dot. So that's 4.7. By the looks of it, 4.7 divided by 5.9 equals, what's that equal? So 4.7 divided by 5.9. 0.796, we can round that to 0.80. 0.80. Right, so that's all the RF's done for that one. Now, one of these, okay, one of these dots, that one, or that one is the same as one of these. So we need to quickly do these measurements here as well now. So that one's coming in at 2.9 by the looks of it, 2.9. So 2.9 is how far that one's run. Now this solvent front is going to be different because it's a different chromatograph. So we need to draw a line through that one as well, and then we're going to measure how far that one has run. So from the top down there, it looks like 4.4 centimetres to me. So 2.9 divided by 4.4 So all these are going to be divided by 4.4 because all A, B and C are on the same piece of paper. Okay, the second one looks like 1.1. 1.1. Now, if you look at this, that's run 1.1 and that's run 1.1. So you may be thinking to yourself, B's the same. Well, we're not interested in how far the dye runs. We're interested in how far the dye runs compares to the solvent front. So it's the result of the division that we're interested in, not the distance, okay, on its own. So that's looking about 3.5, isn't it, that one? 3.5. Okay, 3.5. So we need to divide each of those. And hopefully one of these will have the same answer to one of these, if we've done it right. Let's have a quick look anyway. 2.9 divided by 4.4. 0. We'll round that to 66. 0.66. Next one. 1.1 divided by 4.4. 1.1 divided by 4.4. That's 0.25, isn't it? Okay, and 3.5 divided by 4.4. 0. And we can round that to 80. 0.80. Right, which of these is the same? Okay, well, 0.53 isn't any of those. 0.19 isn't any of those. 0.80, 0.80. So C is the same on both experiments, even though it ran different distances. We're not interested in the distance, we're interested in the distance compared to the solvent front. Okay. Right, which sample is the same both experiments? C. What is the solvent? And is this a stationary phase? The solvent is the water. That's what does the dissolving. And it's not stationary, the water, because the water moves up the paper. So the water is the mobile phase. The paper is the stationary phase, because the paper stays the same. Paper doesn't move anywhere. Okay, so the paper is a stationary phase. Okay, second page on this. Right, explain in your own words how paper chromatography separates a mixture of different liquids. Well, the different dissolved substances, because the dyes are all different and they're dissolved in the water. The different dissolved substances, are the dyes, if you like, the coloured dyes. Because we're doing this, we do this with ink on the core practical. Okay, coloured dyes. The different coloured dyes are different inks in a mixture. Okay, they're attracted to the stationary and the mobile phases. Are attracted to the two phases. The two phases are the stationary and mobile phases. So the paper and the water, in other words, are attracted to the two phases in different proportions. So in other words, some are very attracted to the water, some are very attracted to the paper. And that means they run different distances up the paper. Okay, so that causes them. This causes them to move at different rates through the paper. And every substance moves a unique distance. That's why we can use it to identify them. So we've got another chromatograph here. Okay. Which of these substances, A, B or C, is pure and which is a mixture? Okay, well if we look at A separates into two different dyes. So A is a mixture because we can see two different results here. So that A is a mixture, which we'll put a tick there. B, that separates into just a one, so that's pure. And C, again separating into two, so that is a mixture. Okay. Two of the dyes contain a substance that is identical. Circle this on the substance. Circle the substance on the diagram. So which of these is identical? Well, this one here, A, separates into these two. Now, none of the others have dyes that are moving up at the same height, are we? So we're looking at how high the dyes move. Now, we're all on the same piece of paper, so it's okay to compare things at exactly different heights, or exactly the same heights. So those two, nothing else contains those two. C here, This one, nothing at that height. But this die here in both B and C has run exactly the same height. So those two, okay, are identical. So if these were food colouring, say, if we had 3 food colourings here, A, B and C, and somebody happened to be allergic to this one, okay, would know, after having run this, it was safe for them to eat, food containing dye A, but not B and C, because this one would be identical, if that makes sense. Okay, and that is what we need to know about paper chromatography. As I said, this is a core practical, so there's another video showing exactly how to set one of these experiments up, and watch that if you're not sure about how to do it.